Hello everyone, I'm Priyanka Golia. I'm a joint PhD candidate with IIT Kanpur and NUS Singapore. I'm going to talk about Manthan, a data-driven approach for Boolean function synthesis. This is a joint work with Kuldeep Meel and Shubhajit Roy. So let us start with introduction to Boolean function synthesis. So here we have a Boolean relation f between set of variables x and y, where x is a set of n input variable x1 to xn and y is a set of m output variable y1 to y. For each output variable yi, our aim here is to synthesize a function psi that takes x1 to xn as its input. The bold psi represents a function vector such that if we replace y by psi of x in the relation f, it still holds true. That is, for all the valuation of x for which f of xy evolves to true, f of x psi of x is also evolves to true. Such a function psi is called column function in the literature, and the process of deriving a function from a Boolean relation is known as Boolean function synthesis. So our objective here is to synthesize such a function psi. So just to ensure that we are on the same page, let us consider an example. So here we have x1 and x2 as an input variable and y1 as an output variable. And the relation between input and output variable is x1 or x2 or y1. We can call this relation as a specification also. So our objective here is to synthesize a function psi1 corresponding to the output variable y1. So let us try to rewrite this specification as negation of x1 or x2 implies y1. One can wonder if this negation of x1 or x2 can suffice as a column function corresponding to y1. So let us try to verify that. For that, first we have to compute f of x psi of x. So here we have replaced y1 with its corresponding function negation of x1 or x2. And as we can see here that for all the valuation of x1 or x2 for which f of xy evolves to true, f of x psi of x is also evaluating to true. Hence, this is indeed a column function. But the question arises here is this the only possible column function corresponding to y1? And it turns out that there can exist multiple possible column function. That includes negation of x1 or x2 that we have just discussed, the negation of x1, negation of x2, and it can be just as simple as constant function 1. So there can exist multiple possible column function corresponding to a specification, and our aim here is to synthesize one such function. That's all about the introduction to Boolean function synthesis. Let us move to the application part of it. So the Boolean function synthesis has application in the wide variety of domain that includes certified QB solving, program synthesis, cryptography. We will discuss one such application, cryptography, in detail. The security of well-known encryption algorithm, RSA, depends on the factorization problem. So the factorization problem is, given a number x, we want to compute the non-trivial factor of x. So given an input x, we want to compute the output y, which is a non-trivial factor of x. For that, first we have to write this factorization problem as a relation between input and output problem. So here we have y divides x such that y cannot be the part of 1 or x as it is a non-trivial factor. Here, z represents a set of integer. So now we have a Boolean relation f, and we want to compute a function psi that takes x as an input and gives us y such that if we replace y by psi of x in the relation f, it still holds true. And we can do it by Boolean function synthesis. So that's how we can solve the problem of factorization via Boolean function synthesis. So our objective of this talk is to learn a technique to do such synthesis. So let us move to that. Let us start with state of the art. So the origin of this problem traces back to Boole's seminal work, which was subsequently pursued with the focus of decidability by scholar. The problem of Boolean function synthesis has always been at the great interest of both theoreticians and practitioners. And over the decade, we have seen significant improvement on both the prospect. Theoretically, we know that there exists a problem instance where Boolean function synthesis must take superpolynomial time. Under the complexity theoretic assumption, P not equal to NP. On the other hand, the algorithmic improvement has been driven by a diverse set of techniques. Proof of the validity, the quantify institution in SMT solver, input-output separation, knowledge representation, incremental determinization are some of the techniques that were used in the recent year. Despite being intense algorithmic development over the decades, still there exists a good fraction of instances which are beyond the reach of state of the art. We, as a practitioners, believe that we can do much better. So towards our goal of having better and efficient synthesis technique, we propose Manthan. Motivated by the success of machine learning, Manthan uses machine learning to come up with approximate candidate function. As we all know, machine learning needs data. Manthan does constraint sampling to generate the data. Later, the candidates are repaired using automated and formal reasoning. One thing I would like to emphasize here is, unlike traditional cigar approaches, Manthan learns approximate candidate function, which are later repaired using automated and formal reasoning. So it takes f of xy as its inputs. It first generates the data. With the data generated, it learns the candidate function. And it does a verification check on the learned candidates. Manthan is a sound system, and it will output a function psi only if the candidate passes the verification check. Otherwise, they need to undergo a repair iteration. Let us try to understand Manthan in detail. Let us consider each component one by one. So the first is data generation. We can consider the satisfying assignment of f of xy as our data. But the possible satisfying assignment can be exponential in terms of cardinality of x and y. So we can sample uniformly at random from the possible solution space to generate the data. But the question arises is sampling uniformly at random is good enough to learn a function from a relational data? Let us try to understand this issue through an example. So here we have a specification between x1 and x2 input variable and y1 and y2 output variable. This table here represents all possible satisfying assignment for the specification f. So as you can see here that for a fixed valuation of x1 and x2, the input variable, we can have different valuation of output variable y1 and y2. That is exactly where it differs from the classical machine learning. In the classical machine learning, for a fixed valuation of feature set, we should have exactly one value of label. So if we ask to sample 4 data points uniformly at random from this possible solution space, we may end up getting this right-hand side table as our data. And as we have already discussed, for a specification, there can exist multiple possible column function. And for this specification, there exists a constant function 1 and a constant function 1 corresponding to output variable y1 and a constant function 0 corresponding to output variable y2. With this data, it will be difficult for machine learning to learn a simpler candidate function corresponding to output variable. Can we ask data to help the machine learning? So if we somehow be able to generate these data points, notice the change here. For all the valuation of x1 and x2, we have y1 equal to 1 and y2 equal to 0. So with this data, it will be easier for machine learning to learn a simpler candidate function. So here we hypothesize that just sampling uniformly at random is not good enough to learn a function from a relational data. So towards this end, Manthan proposes adaptive weighted sampling strategy. So it samples uniformly with respect to input variable x. At the same time, it biases the valuation of output variable y. So first it samples a small fraction of data with y biasing towards 1 and y biasing towards 0. With those data generated, it tries to find a good bias Q for the y variable. And then again, it samples uniform for the input variable x and with the bias Q for the output variable y. And that's how Manthan generates the data. Once we have the data, next step for Manthan is to learn the candidate function. So let us consider this specification and let us assume that this is the data we get from the data generation component of Manthan. Just looking at the valuation of I1, we can say that we can consider this problem as a binary classification problem. We can consider the valuation of x1 and x2 as a feature set and the valuation of y1 as a label. And we can learn the decision tree classifier with the feature set and label to learn y1 in terms of input variables x1 and x2. Let us try to generalize this. To learn a candidate function psi corresponding to an output variable yi, we can consider the valuation of x input variables as our feature set and the valuation of yi as our label, and we can learn a decision tree classifier with the feature set and label to learn the candidate function psi. So that's how Manthan learns the candidate. So once it has the candidate function, the next step for Manthan is to verify whether the candidates are the column function or not. So here we can have two cases. The first is when the candidate functions are not column function. So there should exist at least one valuation of x for which f of xy evaluates to true, but f of x psi of x evaluates to false. And if the candidates are this column function, then for all the valuation of x for which f of xy evaluates to true, f of x psi of x should also evaluate to true. So to check whether the candidates are this column function or not, Manthan constructs a formula E over x, y, and y prime variable. We call this E formula as an error formula. Let us try to understand this error formula. So let us look into the second clause of this error formula. So here we have the input variable x same as the specification, but the output is different. So here we have y prime, and every y prime is fixed to its candidate function. So if the candidates are not the column function, then there exists a valuation of x for which f of xy equals to true and f of xy prime equals to false. And so this negation here will ensure that the error formula is set. And if the candidates are this column function, then for all the valuation of x for which f of xy equals to true, f of xy prime also equals to true. And this negation here will ensure this error formula is unset. So as a verification check, Manthan checks the satisfiability of this error formula. If the error formula is unset, Manthan returns as column function psi. So if the error formula is set, we have a counterexample sigma, that is the satisfying assignment of error formula to fix. So we know that when error formula is set, the candidate functions needs to undergo a repair iteration. But the question arises here is, out of m's column functions, which one of those needs to repair? We know that when we fix the value of x to the valuation of x from the counter example, f of xy equals to true and f of xy prime equals to 1. So all the bivariables where sigma yi is not same as sigma yi prime, the functions corresponding to those yi we can consider as a potential candidates to repair. So let us assume that psi I is such a function that needs to repair. So our aim of a repair iteration is to make sure that f of xy prime equals to true with respect to current counter example. So if psi I is giving us the output 0 with the current counter example, we want it to give the output 1. And if it is giving us the output 1, we want it to give the output 0. So to repair its column function psi I, Manthan constructs another formula, gi over x variable and y variable. So it fixes the value of x to the valuation of x from the counter example and valuation of yi as per the output of the current candidate function. And it's tries to find the unset core of gi formula. Basically, it tries to find a reason why, with the current valuation of x, yi cannot take the value as per its output candidate function. With the help of the unset core of gi formula, Manthan constructs a repair formula beta. And using the repair formula beta, Manthan repairs the candidate function. So that's how Manthan repairs its candidate function. So let us try to see the overall picture of Manthan in one frame. So Manthan takes f of xy as its input and it generates the data from the possible satisfying assignments of f of xy. With the data generated, it learns the candidate function psi with the help of a decision tree classifier. And it verifies whether the candidates are this column function or not. To do so, it constructs an error formula and checks its satisfiability. If the error formula is unset, it returns as column function psi. Otherwise, the candidate needs to undergo a repair cycle. So if the error formula is set, Manthan constructs another formula g over x and y variable. And it finds the unset core of g formula to construct the repair formula beta. And with the help of beta, Manthan repairs the candidate. And then it checks the satisfiability of error formula again with the repaired candidates. This loop continues until the error formula is unset. That's how Manthan does the synthesis of his column function. Let us move to the experimental evaluation of Manthan. So we compared Manthan with the state-of-the-art tool CADIT, EFSS, and C2SIM over 609 publicly available benchmarks from diverse suite within a timeout of 7200 seconds. So the plot here represents is a cactus plot with the y-axis being the CPU time and x-axis being the number of instances solved. A point xy represents that x many instances were solved by a solver in less than or equal to y much time. As we can see here that the state-of-the-art tool could solve at most 280 instances out of 609 instances. So where does the Manthan stand? So the green line here represents Manthan. Manthan is able to solve 356 instances, that is an increment of 76 benchmarks over the state-of-the-art tool. Not only just that, over a vis-to-vis analysis with each of these tools, it turns out that Manthan is able to solve 60 new benchmarks that none of the state-of-the-art tools were able to solve. Manthan is not only performing good empirically, but it also opens up several directions for the future work. So here we have hypothesized that just sampling uniformly at random is not good enough to learn a function from a relational data. But what is the ideal distribution to generate the data? We are still far to answer this question. We have found out that the candidate functions learned by decision tree classifier are good in terms of required number of repair iteration. But still we don't have any quantitative measure to measure the goodness of candidate functions. Last but not the least, can we use similar kind of technique to do the program synthesis and program repair? With this, I would like to summarize my talk. So we have discussed about Manthan, a data-driven approach for Boolean function synthesis. Manthan does constraint sampling to generate the data. With the data generated, Manthan uses decision tree classifier to learn the candidates. And the candidates are later repaired using automated and formal reasoning. With this technique, Manthan is able to solve 356 benchmarks. It also opens up several interesting questions for the future work. The tool is available online. Please give it a try. Thank you.